Okay, good day. This is Pre-Calculus. I am Mr. McCully, and this is the presentation for our Blizzard Bag number 1, section 8.1 sequence and series. And the good news is this is way easier than the trig that we've been doing. And it's mostly dealing with integers and positive integers at that. So it does get a little bit easier from here on out, folks. So I'm hoping that we a little bit excited for that. So today we're going to talk about sequence and series. We are going to find the terms in a sequence, both explicitly and recursively. We're going to write an equation for the parent nth term of a sequence, and we're going to understand the meaning of n. Just a little joke there. Get you awake here in the morning. Let's get to it to keep this video short. A sequence is a set of numbers that are related in some way. Each number is an element or a term, and they are usually listed a sub 0, a sub 1, a sub 2, a sub 3, a sub 4. These are all stand-in variables for the elements in the term. They're just numbering those elements. Sequences can be defined defined explicitly, and the way that you do that is give an equation to find the nth term of a sequence. So a real simple example of that, and the first couple questions in the practice work would be something like this, where they're going to say, let a sub n equal, let's just do n squared over n plus 1, something like that. So we have an explicit equation. This little n here tells you what term we're working on. And so if I want to have the first term, excuse me, the first term, a sub 1 would be the first term, and all I do is I replace each n with a 1. So we got 1 squared over 1 plus 1. So the first term in this sequence is going to be 1 over 2, so a half. So there's our first term. And then the next term, a sub 2, would be 2 squared over 2 plus 1, which would be 4 over 3. So the next one is going to be 4 over 3. And then the next term after that, a sub 3, would be 3 squared over 3 plus 1, which would be 9 over 4. So 9 over 4, and I don't think I can reduce any of those fractions. A sub 4 would be 4 squared over 4 plus 1, which would be 16 over 5. And then a sub 5, the fifth term, and most of the questions in the books is going to ask you to find the first 5 terms. That's why I'm doing it that way. You can stop if you want. Nope, that's wrong. N squared over 5 plus 1, which would be 25 over 6. So the fifth term, 25 over 6. And so we can continue that on. So I put a couple dots there to say that that function continues on. All right. Sequences can also be defined recursively. I used to say that recursive sequences kind of are like a loop. And so the way that you do that is you have to have the first few or first one or first few terms given, and as an equation that is based on previous terms. So as a quick example of what that is, we have an example here. This is the first term, and this is the way to find successive terms. So what this says is that the term that you're looking for is defined by taking the term that comes before it. So if this is the fifth term, we're trying to find the fifth term, we plug in the fourth term and then we multiply that by 4. So if I'm trying to find this sequence here, first 5 terms, they already give me the first one. The first one is 4, a sub 1. A sub 2 is going to be defined, so n is 2, is going to be defined by the term before it, so that'll be 1, times 4. And in this case, a sub 1, we already found up over here, so it is 4 times 4, which gives me 16. Now that is the second term. The third term, a sub 3, would be, well, a sub 3, so my n is 3, and then this would be a sub 2 because it's the term before it. Now a sub 2 was 16, or we'll multiply by 4, got to continue. So since a sub 2 was 16, we're going to go 16 times 4, that's 64. So 64 goes right there. A sub 4, well, that's going to be, A sub 4 is our n, or 4 is our n. A sub n minus 1, so that's going to be A sub 3. We multiply that by 4. And so we know what A sub 3 is. We just calculated it. It's 64. We multiply that thing by 4, and we're going to get 256. And I think, I'm not going to use a calculator, so if I make an arithmetic mistake here, you can make fun of me when we get back to class tomorrow, hopefully. A sub 5 would be A sub 4, the term before it, times 4. And 256 times 4, if I think in my back of my head with my powers of 2, which this is going to be 1024. And again, you can check that and give me a hard way if I made a mistake. 1020. Oops, I didn't want to do that. This will be 1024. Okay, there we go. And that also can continue. Now, the Fibonacci sequence is a fairly famous sequence that is defined recursively. It cannot be defined explicitly, which is kind of neat. But we do find that the Fibonacci sequence occurs in nature quite a bit. In fact, if you would like to kind of see something that's a little bit interesting, there's a short little 5-minute TED Talk about the magic of Fibonacci numbers. So just again, I'd like to calculate a couple of these. And so here's my Fibonacci FIB sequence. The first two terms in this sequence are given to you. It's 1 and 1. And so the next term, A sub 3, is defined as the previous term and the term before that. Add that up. So in this case, that would be A sub 2 plus A sub 1. Now, luckily, we've been given both of those, 1 and 1. So let's do it right. 1 plus 1. And so that would be 2. So the third term in the sequence is 2. A sub 4, that would be A sub 3 plus A sub 2. And so, oops, got a call from my wife. A sub 3 would be, let's see, A sub 3 we found to be 2. So it's going to be 2 plus A sub 2, which we know to be 1. And so that one's going to be 3. So 3 there. And A sub 5 is going to be A sub 4 plus A sub 3. She really wants to get a hold of me, but she's going to have to wait. So A sub 5 is going to be A sub 4 plus A sub 3, and A sub 4 was 3. We found that one. And A sub 3 was 2. So we go 3 plus 2 gives me 5. And so I don't need to do a whole lot more work. 3 and 5, the next one would be 8. 5 and 8, the next one would be 13. 8 and 13, the next one would be 21, and so forth and so on. You can continue that on. Okay, so factorials, n factorial. A factorial, to find a factorial, there should be a comma there, I think. I have to ask Mrs. Boyd when I get back. To find a factorial, multiply n by each integer less than n that is greater than 0. So just as a real simple, quick one, 5 factorial, and that's how you read this. Read this, 5 factorial is going to be 5 times 4 times 3 times 2 times 1. And I think I get 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. And there's a way to do it in a calculator, and I will show that when we get back. It's fairly simple. Just make sure you remind me. Just as a special note, 0 factorial is a special case. And because, again, we define our factorials by greater than 0. So 0 factorial is a special case. We just have a definition for it. 0 factorial is 1, and we're going to need that for some calculations, not in this section, but later on. All right. Next, the summation notation. Some of you said that you saw this kind of notation on the ACT, so you want to sign up again for June. But summation notation is basically a way to write the sum of the first n terms of a sequence. This thing I is called the index. This is our counter. The 1, and it doesn't have to be a 1. Sometimes you'll see in the practice work, you'll get a 0 there, and so you'll have to start with 0. That's the lower limit of summation. N is the upper limit of summation. And so this thing right here, this a sub I, it's usually some sort of an explicit definition of a sequence. So it's usually an equation of some sort that allows you to calculate. Now, the way that you do that is you just plug in all the numbers from 1, in this case, up to n, all the counting numbers, all the integers, and then we're just going to add them up. So I want to do a real simple example of this right now. So if I say find the sum for values of I from 1, and we're going to keep it small, to 4 of 2n, or excuse me, I have to use the correct variable, I equals 1 to 4 of 2n, I just did it again, come on, 1 to 4 of 2I, because that's our index, plus 1. And so this thing says take all of the integers from 1 to 4 and plug it into this equation to make your sequence, all right? So I'm not going to do them all, but 2 times 1 plus 1 is 3. So the first number in our series is going to be 3. All right. The next one we're going to is 2, and we're not to our upper bound yet. So 2 times 2 plus 1, well, 2 times 2 is 4. That'll give me 5, and so we're going to add 5 to that. Now we're going to make these calculations all the way through from 1 to 4. So the next one would be 3 times 2 plus 1. Well, 3 times 2 is 6, plus 1 is 7. And then 4 times 2, because 4 is our upper bound here. So 4 times 2 is 8, plus 1 is 9. So the sum of this particular series, 3 plus 5 is 8, 8 plus 7 is 15, 15 plus 9 is 24. And again, I apologize if I made an arithmetic error, but that's the correct process. A couple of properties of summation, and I will do a couple of these. If you have a sum of just a constant, then all you have to do is multiply that constant times the upper bound. If you have a constant times all of your terms, you can factor out that constant and put it in front of the sum. And then if you have the sum of two different equations, you can find the sum of the first equation plus the sum of the second equation separately, and just add those results, and the same thing for difference. And so the way I think of it this way, I'm going to do just this one right here, and I'm going to use the previous example, right? So I have the sum as I equals 1 to n, 2n, and let's make it a value that we can do. Sum I equals 1 to, let's say, 5 this time, and then I'll be okay. So 2n, I keep making that mistake, and I apologize. We'll fix it there. 2i plus 1. Well, using this third property, I can say that that's the sum as I equals 1 to 5 of 2i plus the sum as I equals 1 to 5 of just 1. All right. Now 2i, that thing is going to be, let's see here, if I plug in 1 to all of these values, I'll get 2 plus 4 plus 6 plus 8 plus 10. That's this first one. And then the second one, this first property, since 1 is a constant, I can just simplify that one and use, again, if you have a constant here, it's just that constant times the number, and that makes sense because I'd just be adding up 1 5 times. So 5 times 1, and so let's see here, this is going to be one term more than the last one. 2 and 4 is 6, 6 and 6 is 12, 12 and 8 is 20, 20 and 10 is 30, 30 and 5, this would be 35. And I think that's right. The process is definitely right. All right, keeping it moving here. Finally, consider the sequence: ace of one, or ace of zero, ace of one, ace of two, ace of three, ace of four. Actually, the way I have it defined here, let's just cross this out because I have it defined as ace of one as our starting point. Is the first n terms of the sequence of a finite series, or the nth partial sum, denoted by this expression here. So the nth partial sum is the sum of the first n terms. In this particular instance right here, let's talk about this. This one here that we did in the last one, this represents the fifth partial sum because it is the sum of the first five terms. All right. And we can denote it by that. Now, we're not going to get into any of these until later on, but the sum of all of the terms in an infinite sequence is called an infinite series and is denoted by this expression where you are actually adding up an infinite number of terms. Now, as it turns out, most series diverge and it goes to infinity. Adding up an infinity of numbers usually goes to infinity. But there is certain instances where we will have infinite series that actually converge to a single value, and it's pretty cool. But we won't get to that for at least a couple of sections. Now, I've done examples of most of the practice work already, and so I just want to get into a couple of the more challenging ones before I call time. I'm only at 15 minutes now, which is pretty good. And I should be able to get two good examples in here before I get to the 20-minute mark. And so if you're looking, I am on page, let's see here, 577. And let's see if this is number 40 from the book. And it says, write an equation for the apparent nth term. All right. And so they give us 3, 7, 11, 15, and then 19. And so when I look at this thing, I got to write an equation, and my final answer is going to be a sub n equals something. And when I look at this, 7 minus 3, that has a difference of 4. 11 minus 7 has a difference of 4. 5 minus 11, that has a difference of 4. And 19 minus 5, that also has a difference of 4. So we've got common differences here. And we're going to spend some time with that. But this is just a little bit of hunt and peck. And so we're trying to figure out how we could do that. Well, if my first term, a sub 1 is equal to 3, and a sub 2 is equal to 4, and we have common differences, we can actually write this like a linear equation. And so I'm going to actually find a y equals mx plus b for the point 1, 3, and the point 2. This wasn't 4, I'm sorry, this should be a 7. So that's the second term. The second term was 7. 2, 7. And for this particular instance, I'm going to go the slope. That's equal to 7 minus 3 over 2 minus 1. That gives me, let's see here, 7 minus 3 is 4. 2 minus 1 is 1. So 4 over 1 equal to 4. And then if I go y sub y minus, let's see here, y1 equals m, and we haven't seen this in a while, so I'm writing it out. X minus x1, that's the point slope form. And so we'll just put a point that we know. So y minus 3 equals the slope 4 times x minus 1. Y minus 3 equals 4x minus 4, and then y would equal 4x minus 1. And so this expression right there, that's going to become our equation for this nth parent term. Only thing I have to do is change the variable. So I got 4n minus 1. And we can clearly see if I plug in 1 times 4 is 4 minus 1 gives me 3. The second term, 2 times 4 would be 8 minus 1 is 7. The third term, 3 times 4 is 12 minus 1 gives me 11. So that is my apparent last term. Let's see here. What else do I want? Find the sum. We did one of those. Oh, let's do a factorial one. Let's do one that's got factorials. Okay, I'm doing as my last one page. Let's see here. 578, number 64. That's 64. And they say a sub n is equal to 1 over n plus 1 factorial. Okay. So I'm going to do it horizontally this time because I need to do those calculations. And so the terms, they want me to find the first 5 terms. And this is explicitly defined. So the first term will be 1 over 1 plus 1 factorial. Plus the second one will be 1 over 2 plus 1 factorial. Plus 1 over 3 plus 1 factorial. Plus 1 over 4 plus 1 factorial. Plus 1 over 5 plus 1 factorial. Now this is just going to be 1 over 2 times 1, because 1 plus 1 is 2, and 2 factorial would be 2 times 1, over 1 over 3 times 2 times 1, because 2 plus 1 is 3, and so 3 factorial will be 3 times 2 times 1, plus 1 over, let's see here, and this will be 4, so 4 times 3 times 2 times 1, and then this one, and I made a mistake here. Just it's more a notation error. Since this is finding the first 5 terms in a sequence, I don't need additions. That would be a series. And so I've just made a slight mistake. I'm going to cancel out those plus signs, and I'm just going to put commas here. I'm going to do the same right here. I just don't want to make a mistake longer than when I have to. So I've got another comma there. This one will be 5 times 4 times 3 times 2 times 1. And then this last one will be 1 over 6 times 5 times 4 times 3 times 2 times 1. And so this is 1/2. This is 1/6. And then 6 times 4 is 24. And then we already know that 5 factorial is 120. And then 120 times 6, let's see here, 100 times 6 is 60, or 600. And then 6 times 20 would be 120. So I'm thinking 720. And again, I didn't check that, so you might want to have a go. All right there, folks. That's all I've got for today. We will continue working on this when we get back tomorrow. I am going to email you the link, and then I will also email you guys the new homework assignment sheet for the chapter. Hopefully I'll see you tomorrow. Have a good day. Bye.